Hi there, Miss Barber here. This unit of content is called Mathematics and the Arts. The first lesson is called Mathematics and Music. The learning objectives for this lesson are: demonstrate understanding of wave and pitch as they relate to music and math. Demonstrate understanding of relationship between frequency and vibration, and be able to describe scales and mathematical connections. Let's begin. Sound and music. Any vibrating object produces sound. The vibrations produce a wave. Most musical sounds are made by vibrating strings, vibrating reeds, or vibrating columns of air. One basic quality of sound is pitch. The shorter the string, the higher the pitch. The frequency of a vibrating string is the rate at which it moves up and down. The higher the frequency, the higher the pitch. It is measured in cycles per second, abbreviated CPS. The lowest possible frequency for a particular string, called its fundamental frequency, occurs when it vibrates up and down along its full length. Waves that have frequencies that are integer multiples of the fundamental frequency are called harmonics. String vibrations. Let's observe a string vibrating up and down at illustration A, its fundamental frequency. Illustration B, twice its fundamental frequency. Waves are half as long as those at the fundamental frequency. And C, 4 times its fundamental frequency. The waves are 1/4 as long as those at the fundamental frequency. Music, scales, and mathematics. Raising the pitch by an octave corresponds to a doubling of the frequency. Pairs of notes sound particularly pleasing when one note is an octave higher than the other note. An octave is the interval between, say, middle C and the next higher C. For example, middle C has a frequency of 260 CPS. The C above middle C has a frequency of 2 times 260 CPS, or 520 CPS. The musical tones that span an octave comprise a scale. The Greeks invented the 7-note or diatonic scale that corresponds to the white keys on our piano. Johann Sebastian Bach adopted a 12-tone scale which corresponds to both the white and the black keys on a modern piano. On a 12-tone scale, 2 consecutive notes on the piano keyboard are separated by a half step. For each half step, the frequency increases by some multiplicative factor. Let's call it F. Provided for you is a table that gives the frequencies of notes in the octave above middle C. This table is comprised 4 columns and 14 rows. The first row has the titles note, frequency in CPS, ratio to frequency of preceding note, and ratio to frequency of middle C. Let's read a few rows. The first one is C. The CPS is 260. The 12th root of 2 is approximately 1.05946, and the ratio to the frequency of middle C is just 1. Let's read the second one. C sharp. The tic-tac-toe looking symbol when referring to music is read as sharp. The frequency is 275. Notice it's a little bit above the C. The ratio to frequency of the preceding note is still the 12th root of 2, which is approximately 1.05946. Let's observe. the ratio to frequency of middle C is the 12th root of 2, or approximately 1.05946. Let's just do one more. D in parentheses second. The frequency of D is 292. The ratio to frequency of preceding note is still the 12th root of 2, and the ratio to frequency of middle C is 1.12246. This table will be provided for you on an exam. Example, the dilemma of temperament. Because the whole number ratios in the table are not exact, tuners of musical instruments have the problem of temperament, which can be demonstrated as follows. Start at middle C with a frequency of 260 CPS. Using the whole number ratios, find the frequency if you raise C by a sixth to A, raise A by a fourth to D, lower D by a fifth to G, and lower G by a fifth to C. Having returned to the same note, have you also returned to the same frequency? Solution. Let's do this in order. Raise C by a sixth to A. According to the table, raising a note by a sixth increases its frequency by a factor of approximately 5/3. For example, the frequency of A above middle C is 5/3 times 260 CPS, or approximately 433.33 CPS. Now we'll raise A by a fourth to D. Raising this note by a fourth increases its frequency by 4/3, producing a D with a frequency of 4/3 times 433.33 CPS, which is approximately 577.77 CPS. Now lower D by a fifth to G. Lowering D by a fifth, which is a factor of 2/3, to G gives a frequency of 2/3 times 577.77, which is approximately 385.18 CPS. Lower G by a fifth to C. Lowering G by another fifth, a factor of 2/3, puts us back to middle C, but with a frequency of 2/3 times 385.18 CPS, which is approximately 256.79 CPS. So, did we return to the same frequency? Again, note that by using whole number ratios, we have not quite returned to the proper frequency of 260 CPS for middle C. The problem is that the whole number ratios are not exact. That is, 5/3 times 4/3 times 2/3 times 2/3 is 80/81. It's close to 1, but it is not exactly 1. Example, exponential growth in musical scales. Use the exponential growth law to find the frequency of the note a fifth above middle C, the note 1 octave and a fifth above middle C, and the note 2 octaves and a fifth above middle C. Solution will begin with the note a fifth above middle C. We let the frequency of middle C be the initial value for the scale. So we set Q sub naught equal to 260 CPS. The table of the frequencies show that the note a fifth above middle C is G, which is 7/2 steps above middle C. Therefore, we let n equal 7 in the exponential law and find that the frequency of G is Q is approximately Q naught times 1.05946 to the power of 7. Compute this by using 260 for the Q naught. So 260 times 1.05946 to the power of 7 is approximately 390 CPS. This is a TI-84 Plus CE screen. Let's compute the value using your calculator. For Q0, key in 260, then hit times. Now put in the number 1.05946. For the exponent, use the little caret symbol, key in 7, then enter, and we get the value of 389.5518756, which we round to 390 CPS. Let's continue with that problem. The note 1 octave and a fifth above middle C is 12. Remember, there's 12 half steps in an octave plus 7, which is equal to 19. So 19 half steps above middle C. Letting n equal 19, we find that the frequency of this note is Q is approximately Q0, which we use 260 for middle C, times 1.05946 to the power of 19, which gives us approximately 779 CPS. And now, the note 2 octaves and a fifth above middle C is, we do 2 times 12. 12 for 1 octave, 2 times 12 for 2 octaves, plus 7, which is for the fifth. So 2 times 12 plus 7 is 31. The note 2 octaves and a fifth above middle C is 31 half steps above middle C. We let n equal 31. We find that the frequency of this note is, we write Q is approximately Q0, which we chose as 260, that's the middle C, times 1.05946 to the power of 31, which is approximately 1,558 CPS. The digital age. Until the early 1980s, nearly all music recordings were based on the analog picture of music. Today, most of us listen to digital recordings of music. When a recording is made, the music passes through an electronic device that converts sound waves into an analog electrical signal, which is then digitized by a computer.